जाएगी बिल्ली। मम्मी मम्मी जल्दी ऊपर आओ, अलमारी गिरने वाला है। रुको डंडा लेकर आती हूँ और बिल्ली को भगाती हूँ। अरे मम्मी क्या कर रही हो, जल्दी आओ ना, अलमारी अब गिर ही जाएगा। आ गई डंडा लेकर आ गई। अलमारी गिर गया रे मम्मी। अरे बिल्ली मौसी मत काटना मुझे। अरे मम्मी जल्दी आओ, मैं अलमारी के नीचे दब गया हूँ। अरे चिंटुआ तू अलमारी के नीचे कैसे दब गया? अरे मम्मी ये मत पूछो कि कैसे दबा, पहले मुझे जल्दी बचाओ, मेरे दोनों पैर दर्द कर रहे हैं और बिल्ली भी मुझे काटने वाली है। बिल्ली तू मेरे चिंटुआ को काटने मत, नहीं तो इस डंडे से तुम्हें मार दूंगी। तू मुझे डरा रही है, अब देखो मैं कैसे तुझे डंडे से मारती हूँ। अरे बचाओ रे चिंटुआ। अरे मैं कैसे बचाऊं तुम्हें, मैं खुद यहाँ से निकल नहीं पा रहा हूँ। अरे लगता है उस बुलडोजर के पास एक भी बिल्ली नहीं है। अब चलता हूँ धीरे से वहाँ। अच्छा तो ये छोटा लड़का यहाँ अपना बुलडोजर लेने आया है, अभी बताता हूँ उसे। अब इस कांटेदार कैक्टस को बुलडोजर के सीट पर रख देता हूँ। अब मजा आएगा जब वो लड़का इस पर बैठेगा और ये कैक्टस उसके पिछवाड़े में धंसेगा। अब धीरे से बुलडोजर को लेकर यहाँ से भागता हूँ। बिल्ली तो बहुत ही ज्यादा कटा है। भोले बाबू और चिंटुआ को दौड़ाया और अब ये मुझे काटने के लिए दौड़ा रही है। अरे कोई तो बचाओ रे मुझे इस बिल्ली से। अरे मम्मी तुम कहाँ भाग गई मुझे छोड़ के, जल्दी आओ और मुझे निकालो यहाँ से, ये अलमारी बहुत भारी है। अरे चिंटुआ की आवाज कहाँ से आ रही है? अरे कोई तो निकालो मुझे। अरे लगता है आवाज ऊपर से आ रही है, चलकर देखती हूँ। अरे चिंटुआ तू अलमारी के नीचे क्यों सोया हुआ है? अरे यहाँ मैं सोया नहीं हूँ, नीचे दब गया हूँ। जल्दी निकाल चिंटुआ मुझे। रुको मैं अलमारी को उठाती हूँ। अरे चिंटू ये अलमारी तो बहुत भारी है, मुझसे उठ ही नहीं पा रहा। अरे उठाओ ना जल्दी, क्या कर रही हो? चुप रहो, मैं कोशिश कर रही हूँ ना। अरे चिंटू चिंची और बाबू कहाँ हो? जल्दी यहाँ आओ मेरे पास, देखो मैं तुम तीनों के लिए बड़ा आइसक्रीम लेकर आया हूँ। अरे नीचे पापा आइसक्रीम लेकर आए हैं, अब जल्दी मुझे निकाल चिंकिया, आइसक्रीम खाने जाना है मुझे। किया आइसक्रीम? अरे मैं खाऊंगी आइसक्रीम, मैं खाऊंगी आइसक्रीम। अरे चिंकी मुझे यहाँ अकेला छोड़ के मत जाओ, मुझे भी आइसक्रीम खाना है। अब पापा जल्दी दो आइसक्रीम मुझे। हाँ ये लो।
Vertebrate sensory receptors. Vertebrate sensory receptors reflect adaptations to the nature of sensory stimuli in different external and internal environments. Each environment has chemical and physical characteristics that affect the kinds of energy and molecules that carry sensory information. For example, your external environment consists of the media that surrounds you, the earth that you stand on, and the air that you breathe. Other animals may have different external environments. A trout may be immersed in the cool, clear, and cool, clear, and water of a mountain. Steams or turtle may be submerged on the turbid water of a swamp, and a salmon may be swimming in the salty water of the sea. Each of the previous media contains only certain environment stimuli. For example, air transmits light very well and conducts sound waves rather efficiently. But air can carry only a limited assortment of small molecules detachable using the sense of smell and can pass little or no electrical energy. In water, however, sound travels both faster and farther than in air, and water dissolves and carries a wide range of chemicals. Water, especially seawater, is also an excellent conductor of electricity, but it absorbs and hence fails to transmit many wavelengths of light. As these examples indicate, vertebrate sensory receptors organs like invertebrate sensory receptors have evolved in ways that relate to the environment in which they must function. Many underlying similarities unite all vertebrate senses. For each sense, there is a fascinating story of environmental information. The evolutionary adaptations of receptor cells to detect that information. And the processing in the receptor cells to protect that information, central nervous system of the information so that the animal can use it. What follows is a discussion of particular vertebrate receptors. Lateral line system, ears, eyes, skin sensors that detect changes in the external environment, and of several receptors. Pain proprioception that detects changes in the internal environment of some familiar vertebrate. Lateral line system and electrical sensing, specialized organs for equilibrium and gravity detection, audition, and magnetoreception have evolved from the lateral line system of fishes. The lateral line system for electrical sensing is in the head and body areas of most fishes and some amphibians and platypus. It consists of sensory pores in the epidermis of the skin that connect to canals leading into electroreception skull ampullary organs. These organs can sense electrical currents in the surrounding water. Most living organisms generates weak electrical fields. The ability to detect these fields helps a fish to find mates, capture prey, and avoid predators. This is especially valuable sense in deep, turbulent, or murky water where visions of little use. In fact, some fishes actually generate electrical fields and then use their electroreceptors to detect how surrounding objects distort the field. This allows these species to navigate in murky or turbulent water. Lateral line system and mechanoreception. A mechanoreceptor is excited by mechanical pressures or distortion, sound, touch, and muscular contraction. Lateral line system of cyclostome sharks of the fishes and aquatic amphibians include several different kinds of hair cells. Mechanoreceptors called neuromasts are in pits along the body but not in the head region. All neuromasts are responsive to local water displacement or disturbance. When the water near the lateral line moves, it moves the water in the pits and distorts the hair cells, causing a generator potential in the associated sensory neurons. Thus, the animal can detect the direction and force of water current and the movement of other animals or prey in the water. For example, the sense enables a trout or to orient with its head upstream. Hearing and equilibrium in air. Hearing may initially have been important to vertebrates as a mechanism to alert them to either nearby or far away, potentially dangerous activity. It also became important in the search for food and mates and in communication. Hearing and equilibrium are considered together because both sensations are received in the same vertebrate organ, the ear. The vertebrate's ear has two function units. The auditory apparatus is concerned with hearing and vestibular apparatus is concerned in posture and equilibrium. Sound results. When pressure waves transmit energy through some medium such as air or water, hearing in air poses serious problems for vertebrates since middle ear transforms are sound pressure sensors, but in air sound produces less than 0.1% of the pressure it produces in water. Adaptations to hearing in air resulted from the evolution of an acoustic transformer that incorporates a skin-stretched membrane called either an eardrum, tympanic membrane, and a tympanic membrane and tympanum that is exposed to the air. The tympanum first evolved in the amphibian. The ears of anurans consist of tympanum, a middle ear, and an inner ear. The tympanum is modified integument stretched over a cartilaginous ring. It vibrates in response to sound and transmits these movements to the middle ear. A chamber behind the tympanum touching the tympanum is an ossicle, a small bone or bony structure called the columella or steps. The opposite end of the columella steps touches the membrane of the oval window, which stretches between the middle and inner ear. High frequency 1000 to 5000 Hz sounds strike the tympanum and are transmitted through the middle ear via the columella and cause pressure waves in the fluid of the semicircular canals. These pressure waves in the inner ear fluid stimulate receptor cells. A second small ossicle, the operculum, also touches the oval window substrate. Bony vertebrates transmitted through the front appendages and the pectoral girdle cause these ossicles to vibrate. The resulting pressure waves in the inner ear stimulate a second patches of sensory receptor cells that is sensitive to low frequency 100 to 1000 Hz sound. Muscles attached to the operculum and columella can lock either or both of these ossicles, allowing a frog to scream out either high or low frequency sounds. This mechanism is adaptive because frogs use low and high frequency sounds in different situations. For example, mating cells are high frequency sounds that are of primary importance for only part of the year's breeding season. At other times, low frequency sounds may warn approaching predators. Salamanders lack a tympanum and middle ear. They live in streams, ponds, caves, beneath leaf litter. They have no mating cells and the only sound they hear are probably transmitted through the substratum and skull off to the inner ear. The sense of equilibrium and balance in amphibians involves the semicircular canals. These canals help detect rotational movement and gravity. Since the semicular canals have a similar function in all vertebrates, they are discussed later in this section. In information about the human ear, the structure of reptilian ears vary. For example, the ears of snakes lack a middle ear cavity and tympanum. A bone of the jaw articulates with the steps and receives vibrations of the substratum. In other reptiles, a tympanum may be on the surface or in the small depression in the head. The inner ear of reptiles is similar to that of amphibians. The hearing is well developed in most birds. Loose, delicate feathers cover the external ear opening. Middle and inner ear structures are similar to those of mammal. Auditory senses were also important to the early mammals. Adaptations include an ear flap, the auricle, and the auditory tube, external auditory canal leading to the tympanum that directs sounds to the middle ear. In mammals, the long coiled sensory structure of the inner ear that contains receptors for sounds in the coilia. This structure provides more surface area for receptor cells and gives mammals greater sensitivity to pitch and volume than is present in other animals. Since the structure and function of all mammals' ears are basically the same, the familiar human ear is a good example. The human ear has three divisions: the outer, middle, and inner ear. The outer ear consists of the auricle and external auditory canals. The middle ear begins at the tympanic membrane and ends inside the skull, where two small membranes opening the oval round windows are located. The three small ossicles are between the tympanic. They include the malleus, hammer, incus, annual, and steps. Stirrups are named for their shapes. The malleus adheres to the tympanic membrane and connects to the incus. The incus connects to the steps, which adheres to the oval window. The auditory tube extends from the middle ear to the nasopharynx and equalizes air pressure between the middle ear and the throat. The inner ear has three components. The first two, the vestibule and the semicircular canals, are concerned with equilibrium, and the third, the cochlea, is involved with hearing. The semicircular canals are arranged so that one is in each dimension of space. The process of hearing can be summarized as follows. Sound waves enter the outer ear and create pressure waves that reach the tympanic membrane. Air molecules under pressure vibrate the tympanic membrane. The vibrations move the malleus to